Yeah, okay, so here are the problem statements in the chat. So I guess we'll start from problem one, which so the problem statement's like this. So Bessie and Elsie are playing a game where where they have a pile of S stones, and in each move they can pick some integer X, such that X is not a palindrome, and then they'll remove X stones from S. So they set S is equal to S minus X. And when if a pile is empty when a if a pile is empty when a cow's turn starts, then they lose. The funny thing is that this game is commonly known as NIM, where of course the rules can vary between game to game, but for instance, the variation where each time you can remove one, two, or three um stones at a time, something like that, is a commonly known problem for just like computer science in general. So but in this particular problem, you can remove any number that's not a palindrome. And in particular, they said that leading zeros are not allowed. So as in the statement, they have uh, e.g. 990 is not. Oops, accidentally is not a palindrome. But then they also gave that this 121 or 1 are. So if you don't know where to start with this problem, right, it's hard to know exactly where to jump in. And it's hard to make it's hard to like find a direction of where to go in this problem. Of course, if you've seen something similar before, that can help, right? So, for instance, uh, one of the most important problems when it comes to games between two players is this idea of parity. And th there's or there's a sense in which like we can determine for a given number who is going to win, whether the first player that's going to move on that state is going to win, or the second player that moves on that state is going to win. And there's a sense of parity. So the most important observation for this problem is that in theory, in theory, uh, assuming that LC can, or assuming the second player can win, if the second player can win, then they can win only using numbers from, yes, this is the first bronze problem. They can win only ever choosing X or their palindrome as a number from 1 to 9. So this is the most important observation in this problem, which is that at least only from the perspective of the second player, they can win only using the numbers 1 through 9. So let's see exactly how that plays out and like how that idea is helpful. So for instance, let's consider if we started at say 30. Yes. So say we started at 30. And just like I'm gonna throw this out there that the second player can win from this if the starting pile has 30 stones. And I'm demonstrating that is that like for instance, if Bessie picks to use 11 picks 11 stones out of her pile, we'll be left with 19 stones. And then for instance, Elsie or the second player can pick 9 stones, which leaves us at 10. And it's clear that no matter what move Bessie makes, or no matter what move the first player makes, the second player can choose the number. First player takes X. The second player can take 10 minus X. and it'll be so this will leave us with 10 minus x stones. This will leave us with 0. And then you can see that the first player obviously loses. What just happened? Just broke something. Okay, I'm not quite sure what happened just now. Okay. This is bronze P1. Uh, wait a minute. Sorry. Yeah, so where was I earlier? So I had 30 to took 11 stones. This took us to 19, 9 stones to 10. And we have took x stones to 10 minus x. Then we took, and then we'll take 10 minus x stones to 0. So for instance, and then we can label this. This is, or rather, so I'll label F for the first player's turn and S for the second player's turn. And you can see that, like, for instance, in this particular game, the first player loses, and the second player only ever used stone amounts from 1 through 9, right? And like the point of this observation is you can notice that for the second player, if if initially or yeah, if initially the first player's if initially the last digit of the first player's starting number is 0, the second player can guarantee that that starting number will be 0 by the time the first player acts again. So essentially, if the number is some number of strings and it ends in 0, and this first player takes some number x, no matter what valid x the first player picked, the second player can leave it back to something, something, something ending in 0 for the first player's turn again. Um, and the way they do that is they take this x, and this x will, they can take the last digit of x, and they'll pick the number 10 minus x mod 10. And the way, and how this is possible is because there exists no palindromes that end in 0. So what this means is that if the last digit of the first number is 0 initially, the second player can guarantee that no matter what the first player does, the last digit will always be 0 whenever the first player acts. So it'll be 0, 0, 0, something, and then 0, 0, 0. And you can see that the number is getting smaller over time. So which means that eventually the number will just be 0 and it won't be the second player's turn. It will have to be the first player's turn. So if the number initially ends in a 0, the second player can always win. They can always guarantee a win by forcing the first player to have to make a move starting from the last digit being 0. And the flip side of this is that say the starting value is not 0. Say we have like uh starting a value of 1, 2, 3, 4, 5, right? Then the first player actually can make the situation can make it into a pile where the last number is 0, and they're now the second player. So this is the first player, or yeah, this is the first player, and now it's the second player who has to make the first move on a pile of stones that ends in 0. So what this means is that in the case where the last digit of the number of the initial pile is not 0 initially, the first player can make it 0 after one move, and then the second player will be the one that loses. So after this seemingly complicated explanation, the solution for this problem is simply checking if the last digit is 0. Uh, if S mod 10 is equal to 0, then the answer is else. The second player will always win. And then else Bessie. And at heart, that is just the solution to this problem. Noticing the most important part is noticing that we can conserve the value of we can conserve the value mod 10 of the last digit as the second player. And essentially only the palindromes 1 through 9 count. Yeah, so that's the solution for this problem. Are there any questions or I don't know what's happening to the whiteboard because I don't know why it suddenly turns black, but if not, I'll move on to the second question.